Everyone. My name is Martin. I'm a PhD student here at USC. So I'm going to talk about some of the work I've done in my PhD. Here at USC, literally like 3 buildings across. And obviously, as the name implies, it's relating to generating oxygen out of simulated Martian soils. My advisors are Josh West and Ken Nielsen. And this project was made possible thanks to the Dubai Future Foundation. Okay, so as an introduction, we call it the red planet for a reason. You could see it red with a naked eye from Earth. That says a lot. You got to think of Mars as being a completely and entirely rusted planet, and essentially pretty much the entire planet is covered in what counts as rust, meaning iron oxides. And a lot of the mineralogy has been characterized already with a number of missions we sent over there already. So the main minerals being hematite, magnetite, ilmenite. These are all iron oxides. Now, they contain iron, but they also contain oxygen in their crystal lattice. And that's what Martian soil is made of, or should I say dirt. Now, if we make a couple simple calculations, we can, a couple fair assumptions, given what we know, we can calculate that essentially if we were to extract all the oxygen that's contained in those iron oxides, and we could really pull them out of the rock, we could extract in the hundreds of quadrillions of kilograms of oxygen. That's a lot of oxygen. Now, if we compare that to a system like, say, MOXIE, that's going on to the Mars 2020 rover, that's essentially splitting carbon dioxide from the atmosphere into carbon monoxide and oxygen gas, we're getting literally 3 orders of magnitude less oxygen. That's in a 80-kilometer column of atmosphere versus 50 centimeter of soil around the planet. So again, these are simple calculations. I'm not trying to make real predictions here, but still, even at a conceptual level, I think this really shows that there's the key point here being there's a lot of oxygen on Mars. There's a lot of it, and it can be accessed. It's just contained in the soils, not in the atmosphere. So if you put up with me for maybe 2 slides, I'll talk about a bit of fundamental biochemical systems and a bit of biochemistry. Some of you are maybe familiar with this, some of you maybe not. And the value of this is it'll pay off because it'll really explain the fundamental mechanisms of what systems I've been putting together. So all animals, all metazoans essentially do respiration. That is what we humans do. That is what elephants do, tigers, cockroaches. Any animal you can think of does respiration. And essentially what we take is can I get a? All right, so we take organic carbon, essentially sugar. We combine it with oxygen. And out of this we get carbon dioxide, water, and ATP. ATP is this somewhat stable compound that it just has a lot of energy to it. And if you crack it into ADP, you generate a lot of energy. ATP, all of life on Earth as we know it, uses it. Okay, so it's essentially the energy molecule of life. It's the cache of life. So if you need to do anything that requires energy, like flex a muscle, think a bit, you'll use ATP. And the way we produce ATP is, well, again, humans will produce ATP with respiration, combining sugar, protein, whatever, with oxygen. And the way we do it, we crack that organic compound here, and we crack it through glycolysis of the citric acid cycle. I'm not going to get into the details. And then we produce these intermediates here, NADH for the most part, and we bring them over to the electron transport chain. Now, this is an important reaction simply because by cracking your sugar here, you're essentially liberating all the electrons it has. Okay, so, and you got to think of it this way. Sugar here has a lot of electrons. Oxygen gas, molecular oxygen, is starved of electrons. So this is a bit of an unstable situation. And the idea that you can burn, say, kerosene or burn fat or burn sugar is simply because here you have a high potential energy system to a low potential energy system. So you have something with a lot of electrons, something with very few electrons, and the electrons want to transfer over. So what we do is, in the process, we, in this, what all of us do inside our bellies, we crack all the glucose, the electron-rich material. We transfer those electrons with NADH and FADH2 to the electron transport chain. And we have an electron donor that is linked through a series of enzymes. I'm not going to get into the details. It's kind of complicated, and ultimately ends in oxygen. And we turn that oxygen gas into water. So again, the idea simply being we have an electron donor, goes through a bunch of biochemical wiring, and we have an electron acceptor. And in the process, you have a proton pump, and then you produce ATP. Now, the way to think of this is, again, you have an electron donor and an electron acceptor. That's a battery. That's the exact same thing as a AA battery, or that powers the lights we have. It's the exact same thing as rocket fuel. If you have kerosene and oxygen, you transfer electrons. That's what combustion is. Okay, so that's how the bulk of energy is being produced, and that's how we make a living. Now, the idea with this is humans and tigers, they can only do this, and this only. Take away the sugar, we die. Take away the oxygen, we die. So the idea, again, with this is the idea that we have sugar. This is an electron-rich compound. Oxygen is an electron, wants the electron and wants to absorb the electrons. Now you're measuring energy that can be released out of a transfer of electrons. So you can measure the electric potential, just like a battery again. And this is, if you're not familiar with this, this is essentially an electric potential scale by which, based on a hydrogen electrode, you can measure the electric potential of each compound. And if you can mix, so if you're up there, like glucose, you're a good electron donor. If you're down here, like water, you're a good electron acceptor. If you combine the two in a reaction, you generate energy. Okay, you can liberate energy that we use, life use. Now then again, like I said, if you take away the sugar, we die. If you take away the oxygen, we die. Bacteria aren't like that, though. Bacteria have this, microbes in general, but specifically bacteria have this phenomenal metabolic capabilities that is just unmatched by metazoans. And the idea is simply that if you can combine, again, the same scale here, slightly different picture, but if you can combine any compound that sits high up on the scale with any other compound lower down on the scale, you generate energy. So if you take away sugar and you give, say, hydrogen gas, we can't use that, but bacteria can. Not all, but some will. If you take away oxygen and give, say, manganese oxide, which is literally a rock, we can't survive off of that, but bacteria will. And literally, whatever compound you want to put, hydrogen gas, iron 2, reduced iron, hydrogen sulfide, super toxic for us, right? Some bacterium will use it and combine it with something else lower down and make energy out of it. So really, the metabolic potential of bacteria is really stunning. And in our case, we'll be looking at iron oxides here, and they're not quite as good an electron acceptor as oxygen, but not very far. And essentially, iron oxides, again, being like this rock. They're completely insoluble iron phase that's just a rock. And you can utilize it, bacteria can utilize rocks and are capable of breathing rocks to generate their energy. So it doesn't even need to be inside of them. They can just, respire or respire rocks. And this is what we're going to focus on. So with that in mind, if we're talking about all of life on Earth using a transfer of electron from a donor to an acceptor to generate energy, and if bacteria can take just about anything that's going to give some kind of energy, well, someone, not me, but someone thought maybe 10 years ago, thought, well, how about electricity? Why not give bacteria electricity? And we said, given electric potential, can they use that to respire? And the answer is yes. And you might not think of this as being a microbiology laboratory, but this is what it looks like. This is actually my bench, my own personal bench, again, a couple buildings over, and you got a potentiostat here, and you got a bunch of cultures here with electrodes sticking in and out. And the idea is if you give an electrode, on one end you give a certain substrate, and bacteria will grow on your electrode. They'll break a substrate, feed an electron into the electrode, into the electric system, through the potentiostat or whatever it is, to another set of electrodes, and bacteria will take that electron and transfer it over to somewhere else. And so bacteria can literally breathe electricity and feed electrons or take electrons in and out of an electric system. And this is what, in part, the Nielsen Lab has been working on a lot. So with that in mind, we're getting to where I'm trying to get to here is if we do send people to Mars, or even want to send something back from Mars, we're going to need oxygen, simply because it's a really good propellant in rocket systems. But also for humans, it's really useful to breathe, right? So, and like I said, there's a lot more oxygen, like 3 orders of magnitude more oxygen in soils than in the atmosphere. So the system I had in mind here it all started with this idea is how about we get solar panels and feed electricity onto an electrode, grow some bacteria onto that electrode. The bacteria will take the electrons off the electrode and feed it onto your iron oxide. Iron oxides are known to be good electron acceptors. Schuanella, the bugs we use in our lab, is a really good bug to reduce iron oxides. And so in the process, the question I had was, if you dissolve your iron oxide and reduce your iron, what happens to the oxygen? And ultimately, can we make molecular oxygen off of this. So it's not; these aren't simple answers to get scientifically. It involves electron transfer between two solid substrates, which had never been done before. You need to isolate oxygen gas, also not an easy thing to do because it's just so reactive and just not a stable compound in planetary geochemistry. But after a lot of work and a lot of desperation, this is something that I have. This is what it looks like on my lab, and it's a two-chamber system. And on one, so the conceptual, the CAD essentially of it here, being on one side, you get one chamber where you have your iron oxides and your bugs, and you got your working electrode, you get a potentiostat, and then on the other side, you just have pure water, okay? And on this side, your bacteria will take the electron off the electrode, transfer it over to the iron oxide, in the process reducing and dissolving that iron oxide rust mineral. And that reaction creates a lot of alkalinity, okay? And in the process, you're sucking up protons. So in order to balance the equation, both in terms of stoichiometry, but of charges as well, you need to suck up protons off of the other side, which is just pure water. So now you have, on one side, you have a reducing environment, where a lot of electrons are being dumped. You have an oxidizing environment that's feeding off electrons, taking the electrons out of the system. And you have an alkalinity gradient across proton selective membrane. So that membrane, nothing goes across except protons. Okay. And in the process, you're oxidizing water because it's the only thing to oxidizing and producing oxygen gas. So that's the idea behind it. So if you work on it, on one side you'll have 10 to the 7 cells per mil. Again, this is Schoenella onedensis, cytochrome oxidase A subunit 2 deletion mutant. And you put in current, and then you have some amount of current. You're talking about 4 to 5 microamps. Some amount of this is oxygen. This is current up here. This is oxygen. This is cell density. So we're getting 10 to the 7 cells per mil. It's quite a few cells. It's not that many, but still some. We're getting some amount of oxygen signal. It's not much. It's the low micromolar range, but it's something. But then if you start mixing the system, because otherwise it gets a bit stagnant, and then the proton transfer isn't optimized. So if you start mixing it a bit more, your production rate significantly, your slope essentially here increases significantly. So you're generating oxygen. Oxygen is being made as a byproduct of iron oxide reduction from bacteria breathing electricity. These aren't very big numbers, but if you do 10 to the 8 cells per mil, so that's an order of magnitude more cells, higher cell density, you get a certain amount of current, you start mixing, the current, this is negative current, so it's just a convention. So if the current drops, it increases. So you're increasing current by an order of magnitude if you start mixing it. And same thing, the oxygen increases about 5 or 6 fold. The scales are all the same, so these are all the same scales. So again, you get like low micromolar oxygen. With 10 to the 8 cells, you get up to 40 micromole oxygen. This is what it looks like if you put the electrode onto the scanning electron microscope. So the background gray here essentially is just your working electrode. That's just the electrode. The lighter white stuff here is your iron oxides that are just peppered onto the electrode. And in between, you'll see bacteria here, and they grow these little, not just biofilms, but what we think are nanowires, electric nanowires, which are literally little segments that bacteria can, bioelectric segments that bacteria spit out and can transfer electrons across the length of them. Tad blurry here, but this is optical microscopy on redox sensor green. Redox sensor green is this dye that will bind onto the electron transport chain, that if your cells are actively transferring electrons and doing what they should be doing, they show up as green. And you'll see there's a lot of cells. And this is on the electrode, but if you move up and down the z-axis with a focus, you'll see up and down iron oxides that are settled onto the electrode. And you'll see bacteria peppered and very well successfully colonizing those iron oxides. So your bacteria are transferring electrons, colonizing iron oxides, and reducing iron. We're measuring reduced iron in there, by the way, in the, again, low micromolar. And last but not least, if you do the same experiment with no cells, just a completely sterile environment, you get some amount of current, but not much, and more importantly, you get no oxygen, or at least below detection. So the key lessons from this are really the system works. Okay, this is a proof of concept level system, but the question we were trying to address is, can we use a bioelectric reactor to generate oxygen gas from soils, from Martian soils, essentially extrapolating the oxygen out of soils on Mars? And the answer is yes. We can do so reliably. The amount of oxygen we get is a direct function of cell density. So the more bacteria, the more we have, the more cellular activity we have, the more oxygen we generate, and the more current we generate, electric current. And when we're talking about electric current, we're talking about microamps. Okay, we're not talking about MOXIE. We're not talking about those molten salt reactors that require many kilowatts of energy. We're talking about microamps, which is an extremely minimal amount of current or power or energy. And there's no toxic byproducts, again, as opposed to large amounts of carbon monoxide being produced with MOXIE. And of course, with that, the idea is that, well, the next step would involve scaling it up, maximizing efficiency, I'll talk about perchlorate in a minute, and then ultimately, in the longer term, test and use on Mars. That's the ultimate purpose. Building on this idea, and I think historically, engineering applications have always been very very energy intensive, and never really, or only, well, really seldom make good use of the catalyst that life is. Biotechnologies are barely starting to gain some significant grip in some industries, but Mr. Zubrin this morning had it right, that saying that we have extraordinarily efficient nanotechnologies at our disposal. We are an extraordinarily efficient nanotechnology. Life is just that. Life has this insane ability to catalyze really otherwise improbable reactions. And one of them involves, so again, we're talking about, reducing, dissolving rocks and extracting oxygen out of them by breathing electricity. This other one here involves, I'm not going to get into the biochemistry behind it, but involves perchlorate reduction. If there is maybe 20 to 30 weight% iron oxides in Martian soils, there's 1 to 2% perchlorate salts in Martian soils as well. Perchlorates is very, very toxic. You don't really want to have them. Toxic for us, not for all bacteria. Some bacteria actually breathe them. They're more than happy to use them. And we know, this is from John Coates, the Coates lab in Berkeley. We know that perchlorate reduction is one step. The second step is chloride dismutation. That reaction, it's a normal biochemical reaction that some bacteria do, generates oxygen. And we can measure it, and it's been even shown with a simple but elegant experiment that involved a little balloon here, where if you just have them reduce and dissolve your perchlorates, you're literally generating oxygen gas in that little balloon. So that's another system that we can use to generate oxygen literally out of Martian rocks. There's many other biochemical reactions that we can use if you're interested in hydrogen gas, or for that matter, ethanol, if you like your beer. Fermentation produces ethanol, but also produces hydrogen gas, depending on the pathway. I'm not going to get into it. Another biochemical system here that you have is ammonium with nitrite. You have your electron donor, your electron acceptor here, and you get energy out of this. This is a fairly new system that we discovered maybe 10 years ago. Without getting into the details again, this is one of the metabolites being produced in the process. This is hydrazine. Hydrazine is, if you're aware, is an extremely reactive compound, very toxic for humans as well. It's rocket fuel. Okay, you can use it to fuel. I mean, it's actually the most common monopropellant out there and a storable fuel. So the point here being, if you need a compound, likely there's a bug that can make it. And here in my work and Josh's advisory and Ken Nielsen's advisory work, we've generated oxygen, but really if you care about methane would be archaea, not bacteria, but methane, hydrogen gas, hydrazine, soils, if you want organic material and if you want to grow plants. I think some people are interested in this. You'll need some sort of organic material. And if anything, you'll need something that can synthesize, fix nitrogen or synthesize vitamins, amino acids, these things. Plants aren't always the best at that, and they can use help. So again, if you need it, bacteria can do it. And final statement again being, there's a lot of things that we could use biotechnologies for, but ultimately, in our case, we've successfully proven we can generate oxygen, molecular oxygen, out of a bioelectric reactor, out of essentially bacteria breathing electricity and dissolving Martian rocks. Thank you. I'll be glad to take any questions. Yes, sir.
So how much of the material is freed up? Can you release all of the oxygen, or are you reducing some of it? Or?
At this stage, with my proof. Oh, sorry. Yeah, apologize. Okay. How much oxygen can I release? Essentially, how efficient is the system, essentially, compared to using the stoichiometry here, and if my stoichiometry is accurate, all of it, at least with iron oxide reduction. The perchlorate system, if we only use chloride dismutation, you get only half of the oxygen out of the perchlorate. So the system being as is, the bacteria doing what they do, doesn't mean we can't change it. But for my system, if, again, this is a proof of concept level, there's a lot of questions that haven't been answered about how exactly it functions, what exactly the bugs are doing, and I'd love to do some transcriptomics behind it. But if I do it, if I guessed it right, it's all of it. Because essentially for each electron transferred in the current is electron transferred into AQDS as an intermediate pool and ultimately the iron oxide. And if you have charge balance and stoichiometry, it would be 100%. So I don't want to oversell myself, but conceptually it should be that. But again, I just did this in the past year, so a lot of questions have not been answered yet. Sir.
Where did you find this organism?
Oh, where was this organism found? A good question. That was Ken Nielsen, one of my two advisors, found it, dug it out of a piece of mud out of Lake Oneida in upstate New York. And it goes back like maybe 40 years ago now, but it's been an exceptional lab rat for so many reasons, and yeah, there's decades worth of work on that bug, and it's a really special bug. Well, actually, I shouldn't say that. It's not that special. In terms of the science that's been done on it is special, but we're realizing more and more that there's a lot of bugs that can do these sorts of things. It's just the one that we've been focusing on. Yes, ma'am. That's a good question. What can we do with the iron? If you reduce your iron oxide, you end up with oxygen on one end, and well, on the other end, you have reduced iron to dissolved iron floating around, and you can measure it. I could measure it in some of these experiments. You don't want to, well, for one thing, it's a good nutrient, especially for those extracellular electron transfer systems that Schuanella does. They need a lot of iron for that, so they'll take it to a degree. Ideally, this is a static system where the water just stays in there. You don't want to accumulate too much iron to the extent that it can become toxic if it's in really high concentration. So one of my further longer-term objectives would be to have essentially a steady-state system where water comes in and out in both systems, where on one end you can extract the oxygen and put it wherever you want it, and on the other end you can just get rid of whatever stuff you don't want out of there. So presumably it could, if someone needs iron, dissolved iron, we could give it to someone else, or we could just dump it down somewhere else. I don't know. I haven't thought that far. Sir?
Yes. Have you run calculations to find out how big it would have to be and how much rock it needs to make one?
Okay, so questions about scale. No, I have not. Again, it's a proof of concept level. Again, you could just scale it up, and I definitely want, pardon me for this, but funding permitting, I would love to figure it out. But you could probably grow it as big as you want. Again, it's just a matter of scale. Maybe one more question?
Well, we can take more questions.
Okay.
You can keep asking questions. Just want to check, is Doug Plata here in the room? Doug Plata, he's our next speaker. Well, then we have plenty of time for more questions.
Perfect. All right. Sir? What? Right, what happens to bacteria? So they're perfectly well and fine, and they're alive. Again, if you look at these numbers here, this is total number of cells. I haven't explained it in detail, but total number of cells in the 10 to the 8 cells per mil. These are the number of cells that are electroactive that I can count, so about half of that, so 5 times 10 to the 7, so it's a lot of cells. They just keep on trucking along. As long as I give them electricity, they're going to keep on using it. But, at the end of the day, I have to go back home and cook a meal and say hi to my wife, so I'll just I'll disassemble the material, bleach everything, and then dump it down the drain. Yeah. Not really. No, not at all. Certainly not to human beings. Environmentally, they're pretty benign too, but the standard practice involves bleaching anything we put down. Sorry, yeah. So if there were to be a spill of this system on Mars, what would happen to the bugs? Almost guaranteed they would die instantly. Simply as they are, simply they're just not set up. Especially these bugs wouldn't survive the temperature, the low pressure, and if anything, the perchlorate concentrations. That said, notwithstanding metazoans and humans and the such that are far more complicated, but bacteria can indeed be genetically manipulated quite well at this point. And it's not implausible to think that we could not use not this strain, but a genetically engineered strain that could work in my environment, but also work outside, or this whole different question down the line. But these bugs as is, they're not going to survive Mars, I don't think. Right. Right, so in terms of planetary protection, I think it's been mentioned already by this morning, but if we send humans, it's one thing to send a rover every 10th year or something, and we have ways to try to manage, contamination. But if we're sending humans to Mars, we're sending bugs to Mars. So whether it's Shuanala or another, yeah, it's a whole different question altogether. But whether or not we should make a point to make these bugs capable of tolerating Mars or incapable of tolerating Mars is more of a philosophical or ethical question. Right, so if I keep the same bacteria, yeah. I mean, while they keep on being alive, they don't reproduce that much simply because there's no carbon source, and if you want to reproduce, you need more carbon. There's no carbon source in there. So these won't reproduce that much, especially since they don't have a Calvin cycle. But yeah, I mean, as long as they're alive, they can keep on trucking. Any other questions?
Yeah. What's the doubling time for Shuanala?
Yeah, it's about, well, for this strain, it's a tad slower because it's a CYOA deletion mutant, but I haven't characterized it, and it has been characterized a long time ago, before my time, but in my experience, I'd say maybe 8 hours, 8 to 10 hours. It's still fairly fast. It's not E. coli, but it's pretty fast. Again, there's no carbon source in there, so I don't expect them to reproduce, and they don't seem to be reproducing much. Yes, sir.
On a pure power to oxygen level, how does it compare with a purely electrochemical cell?
Like a molten salt cell? Oh, really? Okay. So how does that system compare to an abiotic electrochemical system? As is right now, again, it's a matter of scale. I can scale it up. If more bugs, bigger electrode, and the such, it's just a matter of scale. But as is right now, I'm getting about 40, 20, 30, 40 micromolar after about, well, depending on how I do things, but anywhere from a couple of hours to 24 hours. I think it's hard to compare because here it's a liquid system, an aqueous system, whereas the electric system involves a molten, well, it's also liquid, but it's a molten salt, not water, system. And I got to say, I know these systems exist. I haven't looked into the literature enough to compare them in terms of productivity rates. Beyond, the biggest thing in my mind was simply the energy demand. And again, where one demands kilowatts of energy just to, and high volt, again, this is 300 millivolts potential. This is absolutely minimal compared to what you typically need to split water abiotically, which is well above a volt. So in terms of energy requirements, I know it's substantially less. In terms of productivity, or activity, I should say, I can't give you a number right now. But yeah, it'd be hard to compare simply because it's just vastly different media and different systems. Yeah. Sir.
What about earthbound applications?
Earthbound applications. Specifically for oxygen, there are some limits. as far as I can foresee right now, in terms of direct applications. Scientifically, it's a whole different system. This reactor is an interesting one for a number of reasons. If you ever watch, some cheesy sci-fi comedy thing, whatever, you'll always hear someone say, "Oh, switch the reverse the potential or reverse the polarity on your system, and it works." This is essentially what I did. Your typical microbial fuel cell involves giving, say, organic material like wastewater, like sugar, whatever, and the bugs will break up the sugar or the wastewater, take the electrons from that, put that into an electric system. In my experiments, I flipped essentially the potential, where the electrons come from the electrode and is meant to be dumped elsewhere. That involves, again, the extracellular electron transfer between a solid substrate to a solid substrate, 2 extracellular substrates. That's never been done before. So scientifically, right there and then, it's like, wow, okay, that's interesting. We should keep on looking this up. What are the biochemical mechanisms? We didn't know that was possible. That was some of the questions I was given when I first pitched the idea, being like, are you sure that's even possible? And I don't know, you got to try. So characterizing more. Scientifically, it's really interesting. Again, in terms of understanding, does that give us an idea as to some of the very, very early Earth ways in which oxygen started to appear in very early Earth? Because then again, we shouldn't have oxygen on Earth. Nowhere. I don't think we've ever detected any oxygen on any other planet, because it's just too reactive. It's too good an electron acceptor, and it'll just react with things. And we should not have oxygen if it weren't for photosynthesis or life. So one of the questions is, especially if you take away photosynthesis, there are precious few ways to generate oxygens. Could this be one of them that might have been something that happened on Earth before the great oxidation event? So, long story short, I think it's mostly a scientific interest for now. That's what I have. Are we out of time? Okay. Well, thanks for all the questions. I appreciate it.